Thanks, Chuck. Thanks to everybody for coming out. I got Jim's permission to do a sort of non-traditional introduction today. I promised at the Nobel Conference when I introduced him to go through the full list of his awards and qualifications, but I got permission to make this a story today because when I saw the title, and you can read it on the screen, Symmetry and the Quincunx Nexus, I thought, that's going to scare him away pretty good. Not much of an audience is going to turn up. And then I decided, well, maybe it sounds like the title for an episode of Big Bang Theory, so maybe they will come, because often we look at the titles of those and have no idea what they mean, but they're kind of funny. And so I have to tell you that I have no idea what the Quincunx Nexus is. I have no clue, and you probably don't either. So I don't know that, but I do know something that you don't know, and that's what the story I want to tell you today. Almost exactly 10 years ago, the summer of 2003, I was at a meeting in Madison, Wisconsin, a physics teachers meeting, and I attended a talk, the first time I ever heard Jim Gates speak. And at least the subtitle of the talk was, Why Einstein Would Like Spaghetti. And I knew nothing about string theory before I heard that talk, and after that talk, I was so enthused about string theory and about Jim Gates that I ran out on the steps of the convention center in Madison, struggling in my wallet to find one of my business cards, found Professor Gates, ran up to him, introduced myself, handed him the card and said, please, please, we have this thing called the Nobel Conference at Gustavus. And I don't know if you know about it or not, but please consider coming to speak at one of our conferences, because I had never heard a talk that took something so, I guess, complicated and esoteric and brought it down to a level that I thought anybody could understand. Well, we were fortunate enough 2 years later to convince Jim to come here and be a part of the 2005 Nobel Conference on the legacy of Einstein, in which he gave a fabulous talk that was very, very well received. And 2 years after that, we were really lucky enough to get him to come back in his first stint as the Rydell Professor. And in 2007, Jim and I team taught a course on string theory, not for physics majors, but to a general education audience. So we had students from freshmen through seniors, most of whom were not science majors, who spent a semester learning about string theory from Jim. And I certainly learned about string theory. So what I learned through those experiences that you don't know, but you're about to find out, is that this is a person who can take the most cutting-edge, deepest theoretical, mathematical physics and teach you something about it, make it make sense to you, and have you and let you understand what its significance is. So I am absolutely delighted that Jim has agreed to both come back and speak at this year's conference and to be our Rydell Professor again. So please welcome Professor Jim Gates.
Well, thank you for coming out, even though you don't know what I'm about to tell you. It's a great pleasure to be back here at Gustavus Adolphus, as well as in St. Peter. One of the things that I was afraid Steve was going to tell another story. So I'm going to tell that one as my introductory remark. So what Steve didn't tell you was that after the Nobel Conference, I brought my entire family, my daughter, son, and wife back here to St. Peter because I personally just fell in love with St. Peter. I think this is just such a very special place. And 2 days ago, when I was discussing the fact that with my wife that I was coming back, she said, and I don't get to come. And I'm like, no, I'm having all the good stuff to myself this time. So I'm really, really very, very happy to be back here at Gustavus and St. Peter and look forward to coming back several times as the visiting Rydell Professor this year. Let me start my presentation not on the subject of the talk, but by making sure each and every one of you knows that I am not Morgan Freeman. Now, you obviously got the joke, but you see, there's a lot behind that joke, and that's the story I want to tell before getting started. So about the time that I was here as a Rydell visiting professor, I also traveled a lot around the world, and I was coming back from South Africa, and I sat down I was trying to make my way to a seat, and as I approached my seat, there was a gentleman in the aisle seat, and he looked up at me and had the brightest smile, and I was like, wow, what a friendly guy. And he introduced himself in his South African Afrikaans accent. And I was trying to get my luggage up in the overhead rack, and he said, "Can I help you?" And I'm like, "Sure." So he helped me get my luggage up, and then I sat down and opened up my computer, and out of the corner of my eye, I could see he was still smiling at me. You know, if you meet someone you've never met before, they're busy staring at you smiling, you start to get a little bit uncomfortable. So I turned and said, "Can I help you?" And he said, "Come on, we all know who you are." And I'm like, I can't believe that science documentaries are that popular here in South Africa. Because by now I've done about a dozen, and they do go all over the world, and I'm like, but then I thought, no, that can't be it. And then I turned and I said, "So what films have you seen me in?" And he drew back and said, "Why, Invictus, of course." And that was not the first time that I've been misidentified as Morgan Freeman. I am not Morgan Freeman. Now, I hope to meet Morgan Freeman one day and have someone take a picture so that the next time someone says, "You're Morgan Freeman," I can whip my picture out and say, "Me? Morgan. Not same." So let's get started with today's discussion of science. And we'll try to make clear this strange title as we go through it. So there's me a few years ago. As you can see, my hair was a lot longer and darker. And if you look at this picture, one of them may look slightly different to you. One may look better. I'm going to ask you to look for a few moments and decide which one you think looks better, right or left. We'll come back to that. So it turns out that we humans are very, very, what appears to be almost genetically coded to be sensitive to symmetry. When we look at a picture, if it's balanced somehow aesthetically, it's a more pleasing picture to us than if it's sort of one-sided. Our whole notion of beauty, in fact, seems to be connected to symmetry. So symmetry, as we scientists talk about it, we can go back even to ancient Greece, and there's this funny number called the golden ratio. So let me talk about this number. So here I've drawn a line. I've drawn two lines, a red line and a blue line. Now, each of them has a length, and if I had a ruler, I could measure that length, and that would give me some numbers for each one. So let me imagine that I measured those two numbers, and then what I do is I put the red one, which is the short line, over the long one. That will give me some fraction, right? And now let me form another fraction by taking this number and putting it on top of the entire length. That will give me, in principle, another fraction. So suppose I demand those two fractions are equal. Because in mathematics, that's the kind of stuff we do. It's algebra. If you do that, you get led to this very peculiar number, which you see at the bottom here. It's called the golden ratio. And it's possible, there's some suggestive evidence that we humans have actually been aware of this particular number for a very, very long time, even though we might not have consciously known it. And it's connected to symmetry. So you see, here I did it with line segments, but you see I can do the same thing with areas. On the bottom here, I have two boxes. I can measure that area, I can measure that area, and and those are two numbers, I can form a fraction. Then I can take the larger box here, and that's a number, and place it over the area that comes from all of it. That's again a fraction. And if you say they're the same, you get the same golden ratio. The golden ratio shows up actually in lots of very strange things that humans do. Here's a picture of the Parthenon. And if you actually look in this picture, you can actually see sort of the golden ratio emerges, because here are two boxes that I told you about, the little one and the one that's a little bigger, and have them that same number. But then you could say, well, gee, suppose I take the sum of these two and say demand that that be the same fraction over here. I can take this big piece, look at a part down here that has the same ratio. I can keep doing this over and over again, and the strange thing is that the ratios that you get this way look like the proportions of the Parthenon. So it looks like Even though the Greeks may not have consciously been aware of this number, their sense of beauty led them to this number. Now, it turns out there's another way to think about this number. Here's a sequence of numbers, 1, 1, 0, 2, 3, 5, 8. You know, just a bunch of numbers. Look like it's random. But in fact, there's a pattern here. What's the pattern? Well, if I add these two numbers together, 0 and 1, it gives me 1. If I add 1 and 1, it gives me 2. If I add 1 and 2, that gives me 3. If I add 2 and 3, that gives me 5. And so we see a pattern for how to keep getting bigger and bigger numbers. This is called the Fibonacci series. It was known to the Italian mathematician Fibonacci, and it appears in a book that he wrote in 1202. Now, it turns out that if you look at these things, you can again form fractions, right? For example, I could take this number, the 5, and think that put it under 3, I form a fraction. I could take the 13 and put it under an 8 and form a fraction. Or I could take the 144 and put it on an 89, I form a fraction. So let's imagine that I do this over and over again as I look at all these numbers. It turns out that as you get out there to a million digits or so and look at that fraction, guess what number it is? It's the golden ratio. So the golden ratio shows up in weird places in architecture and just algebra, and now we see that it's even in numbers, somehow the golden ratio is special. And it seems to show up in nature in other ways. So here we have a nautilus shell, and if you actually look at the curve that winds around inside to the outside of the nautilus shell, and then compare that. Here's a picture of the Parthenon I've turned on the side. And you wind around here, which we can actually see illustrated. It looks frighteningly similar to a nautilus shell shape. Again, it looks like nature somehow has a preference for the golden ratio. Now, that's not quite true, but it's approximately true even in nature. This same number, by the way, governs the way, if you look at the growth of leaves, of branches on trees, you find the same number shows up. So this number is like hidden in nature, and it's all around us, even though we're not aware of it. And so it's got something to do with balance. Well, you know, the Greeks did lots of stuff, and there's this notion of Platonic solids, 5 special solids. And they're called the Platonic solids, and let's talk about how we build these things. So this you can think of as a pyramid where all the sides are the same. We call it a tetrahedron. Everybody knows a cube. How do you build a tetrahedron? Well, you take a triangle, and then you build on the side another triangle that's identical to the first, a second, and then you put a bottom on it, and you get the tetrahedron. So it's something that all the sides are the same. You can do this not just with triangles. You can go to the next figure, which is the square. You can take a square on each side, build a square, and then build up a cube. You can start with a pentagon and build up an object. And so these are the Platonic solids. And it turns out there are only 5 of these things that you can build. You can't do this forever. Not every shape works. Only 5 shape works. And now, the most interesting thing of these 5 shapes are the biggest ones. The biggest ones are called the dodecahedron and the icosahedron. The dodecahedron is the shape we see here. Imagine you're a tiny person that was inside of this shape. Then you would see this object all around you, and you could point your finger at the center of one of those faces. You could take your other hand and point to the center of the adjacent face. There's an angle between your 2 arms. Guess what that angle is? It's the golden ratio. So the golden ratio shows up in the Platonic solids, and as I said, the most complicated Platonic solid is this thing called an icosahedron, which has 5 triangles, 20 faces, 12 edges, but it's the golden ratio. So the golden ratio is it's like magically available in nature. It's magically available in numbers, and it seems to have something to do with our innate sense of balance and symmetry. So this is the math of proving the statements. And I know you're not all math whizzes, but if you sit down, you can do these calculations just like on the Big Bang and get these results, showing that the golden ratio shows up. Well, we talked about symmetry. It turns out that symmetry, the search for balance, is one of the tools that science has been using for about 500 years. And one of the people who first really pushed this idea was Johannes Kepler. Because at the time that Kepler was alive, the only planets that were known were Mercury, Venus, Earth, Mars, Jupiter, and Saturn. Nobody knew about the rest of them. And the question became, these planets orbit the sun at different distances. Why at the distances that they do? And he had a brilliant idea. He said that it's the perfect solids that control this. So how does it work? So you build a big ball, which you can see here and are illustrated, and then inside of that you put a cube, which is one of the perfect solids. Then inside of this cube you put a smaller ball that just barely touches the edge of the cube that you've inserted. Then inside of that you put the tetrahedron or the pyramid. Then inside of that you put a tiny ball that just barely touches the side of the pyramid. And then you put inside of that the dodecahedron, the icosahedron, and then you use up all the perfect solids. Now there are only 5 of them, so that means you can only do 5 of these balls. And now what Kepler said is, you see this distance out here, away from the center of this construct? He said that must be why Saturn orbits where it does. You move to the smaller ball, it's here. It's, again, some distance from the center. Kepler's idea was that distance, which is the orbit of Jupiter, again, was controlled by this ball, whose shape was controlled by the perfect solid. And so he had this model that we could understand our solar system by knowing about the mathematics of the Platonic solids or the perfect solids. It's a beautiful idea. One of the most beautiful ideas that I remember when I learned about it, one of the most beautiful ideas I've ever seen. There's only one little problem with it. It's wrong. Beautiful, but wrong. First of all, it's wrong because it doesn't take into a couple of more planets like Neptune, Uranus, and then the thing that may or may not be a planet called Pluto. Because remember, it got demoted. You know, when I was a kid, it was a planet. Now people say it's not a planet. Who knows in the future, maybe it will be a planet again. We don't know, right? So we didn't know about those planets at the time that Kepler was wondering about the universe. And so they were left out of this construction. If he had known about them, then he could not have pursued this idea. Now, one of the interesting things about his idea that this allows us to understand the orbits of the planets is that he was in love with this idea. And as I said, I think it's an extremely beautiful idea. But he abandoned it. And the reason he abandoned it turns out to be interesting because it tells us something about how science works. You see, we scientists basically make up stuff. My wife is a doctor, and oftentimes she meets people and they ask her, what does your husband do? Or they find out her husband is a physicist and say, what does he actually do? And her answer is, he makes up stuff for a living. But since it's mathematics, no one can tell him it's wrong. There is an element of truth to that story, but not completely. You see, what theoretical physicists do, which seems mysterious to many people, is actually rather similar to what novelists do. You know what novelists does. They take words and letters and punctuation and they tell stories with them. Theoretical physicists take mathematics and we tell stories with them. But whereas a novelist is determined to be good or bad by the nature of the audience reading the work, a theoretical physicist is determined to be good and bad by the audience of nature and how accurate the things we make up describe how nature works. That's what makes a good theoretical physicist. So yeah, we make up stuff. Most of the stuff we make up is wrong. And the way that we sort that out is that we go to nature and say, this made-up story that I have, does it match to something that you can measure in the laboratory? That's what there's a word attached to that. It's called experiment. But all we're doing is matching our stories, the stories we make up. We're just matching them against measurement. And we say nature then makes the call. That's the secret of science. Now, because that's the way science works, it tells you a couple of interesting things. You see, Kepler understood that nature makes the call. No matter how beautiful the ideas, how much we love them, nature makes the call about what makes for good science. Not any person, not any person's aesthetic beliefs, nor any other form of belief that humans may hold. That's not what determines science. We make up the stories. Nature determines whether it's good science. Now, I don't know about you folks, but in our country, as a population, we're often very confused about science. And one of the ways that people like me see that is through the debate around global climate change. There are large numbers of Americans who think that it's a plot that was dreamed up by Vice President Gore so he could win the Nobel Prize. He did get the Nobel Prize, but he didn't dream it up as a plot. All the evidence that we scientists can amass tells us, A, that global climate change is happening. And people say, oh yeah, but temperatures change all the time, so why do you say it's us that's doing it? Why is it that we're the culprits in this story? And the answer turns out to be, yeah, temperatures change all the time in the geological history of the planet, but they never change on the time scale that we've seen here. In about 200 years, we have dramatically changed the temperature of the Earth. At no point in history in 200 years can you find a magnitude of change like this. That's why we're convinced we're responsible for this stuff. It's not something natural that's going on out there, nor is it a plot. Now, what we do about it, we live in a democratic society, and collectively we're going to have to decide what's the appropriate action. But to make the claim that this is not scientific is not, if you say that to a scientist, we'll tell you, you don't know what science is. Because scientifically, the evidence, it is no longer under debate. We're responsible. So that's part of the nature of science. It brings us things many times that we don't want to hear. But that is, in fact, part of the nature of science. We let nature make the call. So in our sense of telling stories, one of our big guiding points is to look for symmetry, to look for our innate sense of balance, because it often turns out that the internal aesthetic that we have around balance leads us to find new results in equations, first of all, which then we match against nature, and if we're really good, we get new answers we didn't know about. There's an example of this that played out in the 60s called the Eightfold Way. Here's a picture, and you look at it and you say, yeah, that's a pretty balanced picture. For every piece on the left, there's a piece on the right. For every piece that's up, there's a piece that's down. Looks pretty balanced to me. And that's essentially what we physicists mean by symmetry. Now, it turns out there's some deep mathematics that are associated with this picture. In particular, there was a mathematician named Sophus Lee who taught us how to take these kinds of pictures and turn them into a subject mathematicians call group theory. In the 1960s, while doing experiments on nuclear matter, people started to find objects. Well, even beforehand, we knew about the proton and the neutron. That's the P at the end that's up here. But in the 50s and 60s, we started doing experiments as a species on nuclear matter, and we found out there were more and more forms of nuclear matter than we had known about. There's not just a proton and a neutron. There's lots and lots. In fact, there are over 200 known particles that are nuclear matter now. And so when you see something like that, it begins to look like a zoo. And so you might start to scratch your head saying, well, gee, how are all those, let's call them animals, how are all those animals related to each other? Well, one thing you might do is to try to put them into families. Just like, there's a canine family in biology, and it includes dogs, but it also includes other animals that are canines. There are felines, right? So we know in biology that when you see a complicated array of objects or things or entities or beings, one way you can try to bring order is to put them into families, try to figure out the relationship. So when these new forms of nuclear matter were discovered in the 50s and 60s, physicists did the same thing. And what they found, and principally a physicist by the name of Murray Gell-Mann is the person who had this realization, what he found was you can arrange a family so that these triangles, so that this figure shows, and it involves triangles. Now, it's called the Eightfold Way because there are 8 nuclear particles in this. The proton and the neutron you see at the top. There are things called sigma particles, which the person who introduced me a few moments ago can tell you all about, because that's what he did when he was in graduate school, study some of that stuff. And then there are xi particles at the bottom, and if you count, there are 8. And you can see the triangles. You can see there are triangles in this diagram. So triangular symmetry, this is the crazy thing. Just knowing about triangles has a story to tell about nuclear matter. That's the message. It's one of these wild leaps that we see in physics, that something that you would have never thought of, simple triangles, things that we have played with when we were in grade school, has something to do with nuclear matter. Who could have thought of such a thing? That's the kind of universe we live in, where those kinds of coincidences occur. Here's another such picture with a different family. And this family is actually very famous in physics because once Gell-Mann worked out that these triangles had something to do with nuclear matter, he could make predictions that no one had seen before. In particular, here you can to see the triangles, you have to draw lines like this. You can see if I do this, there's a triangle there. And if I move my cursor like that, there's a triangle there. So there are triangles buried in this image. So at some point in the 60s, all of the particles at the top part of this were known, had been discovered in the laboratory. This thing at the bottom wasn't known. Now, if you look at this picture, you can see if you put the bottom particle here, there's this one last triangle. And because Gell-Mann was one of the few physicists in the world who did understand this mathematics, he said, if you go to the laboratory and do an experiment, you will find a new piece of nuclear matter that fits at the head of this triangle. In other words, he did exactly what Kepler was doing, taking a nice, beautiful picture and using it to try to understand something very complicated in nature. But unlike Kepler, Gell-Mann got it right. After about a year of making the prediction, people went to the laboratory and they found this object. And that's why we physicists became very interested in what's called group theory and Lie algebras. It's because inside of nuclear matter there are quarks, these little red dots. You can think of them as little tiny things that sit inside of protons and neutrons. In the real world, this is a cartoon of a proton. The quarks are inside, and I can try to pull one out, but in fact, I'm never quite able to get it out. It turns out that these things like to stay inside of nuclear matter, even though we have the mathematics to describe them, even though we've done lots and lots of experiments that actually tell us they're inside of nuclear matter, we can never actually pull them out to examine them in the world around us. But the fact that they're there has consequences, and we've checked those consequences. One of the places this occurs is at the Large Hadron Collider in CERN. This is one of the parts of the science they do there. And it's all based on mathematics. At the top here, I've actually written some of the equations that tell these stories, because we physicists get our stories from the mathematics we write. Remember, that's how theoretical physics works. We are novelists, but our tool is mathematics. So we learn about the universe this way, by combining our innate sense of balance and looking at pretty pictures and then trying to match to see if that tells us a story about something that we didn't know about in nature. And it turns out in our world, yes. In our world, there's the electron, which was actually known about in the 1800s. Nature actually has a copy of the electron that's 200 times heavy called the muon, and then she has another copy 1,700 times as heavy called the tau particle. And yet, in some way, all of the things here are, in some sense, like the electron. The tau and the muon are heavier than the electron, but they have exactly the same charge. These things called neutrinos are like the electron, but they're much, much lighter, about 10,000 times lighter. 10,000 approximately. But they have no electrical charge, and yet in many ways they look like the electron. I told you about the up and down quarks that were inside of protons. Turns out those are only the first two of a member of 18 such objects. Looks like there are 18 quarks in our universe. This is the kind of science we uncover at CERN. And in our universe, there are objects that carry forces from one location to another. The photon is the most familiar. And then on July the 4th of 2012, we learned about something new called the Higgs particle. It was discovered at CERN, and again, it's something that we had never seen in the laboratory before, but that someone, a guy named Peter Higgs among them, wrote a set of equations that had this balance property, and it told him that if you look for this object, it's somewhere in nature. Now, this may sound rather interesting to you because, you see, a lot of people think that science works as follows. Science, they think, is like a safari. You know how safari works. You pay lots of money to go to someplace you've never been before. You then look out the window and you see a new animal or a new bird that you've never seen before. And so a lot of people think that's how science works. You build a big, complicated device, you turn it on, and you go out to look for something new. That's not how science works, not this kind of science. You see, when you start talking about ultramicroscopic particles like quarks and electrons and things like that, first thing you have to figure out is when you've seen something new, or if there's this new thing there, what kind of signal does it produce? Because it's so complicated down there at these small scales, you have no a priori sense of what is there. And so it actually turns out that in order to find things like the Higgs particle, you actually first have to be able to predict the kinds of signals the Higgs particle would produce. And then you go look for those signals. And that's what happened with the Higgs boson in 2012. There were certain signals that were predicted by the mathematics that Higgs started off, Higgs and a number of other people, Anderson, Guralnik, Hagen, Higgs himself, Kibble, Tooft. There's a whole bevy of people who did it, but we use Higgs because he actually said, go look for the particle, and no one else did. These tiny things spin like little tops. So quarks spin like little balls, but they're funny because you can't speed them up or slow them down. And in fact, we physicists, there's a missing square here. We physicists have a number which describes this rate of spin. So the Higgs boson basically comes from this story. Look at this picture. I claim it's a balanced picture. Why so? Well, you see three objects at the bottom. They're all about the same size. They're spread evenly across the bottom of the diagram. There's an object in the top. Well, it's there by itself, but it's in the center of the picture. Very balanced picture. It turns out that the three dots on the bottom actually represent things that we see in nature. One of them is the photon. The other is what we call a W particle, which is a form of force carrier that causes natural radioactivity like uranium. And the other object here is something called the Z boson. And so this is a balanced picture. And yet, this picture is so perfectly balanced, it cannot actually be our universe. You see, in our universe, the electromagnetic force, which is carried by the photon, is different from the weak nuclear force. So in our universe, you have to try to make these things somehow different. And yet, in the 1950s, when people tried to do the mathematics to make these things different, they were led to things that embarrassed people like me. They were led to mathematical inconsistencies. Because you see, one of the rules about theoretical physics is that it's got to be mathematically correct. You can dream up any story you want to, but it's got to be internally mathematically correct. It cannot be illogical. And so, experimentally, you say weak nuclear force has got to be different from electromagnetism. In terms of your mathematics, if you try to make it different, you are led to an inconsistency. And so what Higgs and this other bevy of physicists actually did is they told us the following is the way nature really works. They say start with the balanced picture where this object, Start with the balanced picture where this object called a Goldstone boson is indeed balanced at the top of the hill, but let it roll down the hill, and my animation seems not to be cooperating with me. But as this object were to roll down the hill, it interacts with these, and in fact what it does is cause the W and the Z particle to become massive so that the equations obey the kind of laws we see in the laboratory, and it leaves the photon without mass. And so it obeys the kind of laws that we see in the laboratory. That was why the work of Higgs will probably, many of us think, get him a Nobel Prize very shortly. Because he's the person who put it all together to tell this story. Now notice it's a story that I told you. I didn't show you any equations. It's a story. That's the best of theoretical physics. It's about telling stories. The other thing that this Higgs boson does is it gives mass to the electron, and it does it in the way that this picture shows. We imagine that things like electrons, let me back this up and start over again, that things like the electrons, which here are represented by a ball, move to the presence of the Higgs boson, and that's how we get their mass. To find this stuff takes billions of dollars. So the Large Hadron Collider, we Americans are not there in a certain way because it's in Europe, it's in Geneva, but there are several thousand Americans there because you see, we built the big iPhones that are the cameras that took pictures of the Higgs particle. Now, we don't call them iPhones, we call them detectors, and we're going to talk about those things. But the detectors that found the Higgs is your tax money. It is at least a minimum of $600 million. It is Americans who built the devices. It is Americans who operated the devices. It is Americans who found the signals first. So although many people say, gee, the Europeans are out there outstripping us in science, we actually made a contribution here that was critical, and it would not have happened without Americans. This is a computer simulation. Remember I told you that you have to know what the signals look like in order to go find the thing? This is a computer simulation that was constructed from the mathematics describing this story about the rolling ball down the hill. It says that if you do a collision, you should see a pattern like this if there's a Higgs particle. So we use computers to actually generate these signals, and then we go to check to see if we can find them. So the discovery of the Higgs boson in 2012 was the first item on my bucket list. So even though I'm not Morgan Freeman, I do have a bucket list. As a theorist, there are 4 things I would love to see before I'm no longer thinking about physics. One of them is the Higgs boson, and on 2012, July 4th, it was announced we saw it. The next thing is waves of gravity. Gee, you've never heard about waves of gravity, but if you go back, for example, and look at our Nobel lecture from the previous Nobel Conference where I'm a speaker, I actually talked about the waves of gravity there. So you can go online, and if you'll just type Gustavus and Jim Gates or Nobel, you'll be able to see the entire talk. But we think that there should be waves of gravity. You should scratch your head. Waves of gravity? I've never heard of a wave of gravity. Gravity just pulls stuff down. It doesn't wave. Well, according to Einstein's equations, yes, it does. That there are conditions under which gravity forms waves. Now, we haven't seen this, and there are laboratories looking for it. But again, it's one of these stories that comes out of our mathematics. The other thing that I would hope is to be alive when superpartners are found, and we're going to talk about what those are. And then finally, there's this little thing called string theory that people talk about from time to time, that people like me think may in fact be an accurate description of our universe. But until nature has her ruling on this, we don't know. We do know it's mathematics. We don't know if it's science. So what is supersymmetry? Well, in supersymmetry, so if you take particles of light, they can actually pass right through each other. Now you can actually prove this. Just take a flashlight, get in a room with a lot of dust, turn on the 2 flashlights, the 2 beams of lights pass right through each other. So particles of light have the property they can pass through each other. Suppose you tried this for 2 electrons. They wouldn't pass through each other. Why not? Well, first of all, if you know something about like charges, you know like charges repel each other. And so as you try to put 2 electrons in the same place, the force of electromagnetic repulsion gets stronger and stronger, and it pushes them apart. But you see, in a world like mine, where mathematics is how I see the universe, we theoretical physicists use mathematics as a tool of perception. It's a perception organ for us. In our world, we know how to turn off the electrical charge for electrons. It's changing a term in an equation. And so we can change a term in an equation and ask again, can you make 2 electrons pass through each other when we have turned off the electrical charge? The answer turns out to be you can't. So our universe apparently has 2 different kinds of objects in it. It's got things like electrons where you can't make them pass through each other even if you turned off all the electrical repulsion. And then it has things like photons, particles of light, which freely pass through each other. Now, we give these 2 classes of things names. We call the things over here, we call fermions. Things like the electrons are fermions. Things like the particle of light is called a boson, and yet these are 2 fundamental attributes of our universe. One of the interesting things about photons is that they carry forces, and in fact, all the force carriers have this general passing through ability if you turn off a charge. Electrons, quarks, protons, all have the property that even if you turned off the charges, they don't pass through to each other. So we see, if you stop and think about it, it means our universe looks like this, where you have a bunch of things that pass through each other, they have very different properties, then a bunch of things that don't pass through each other. My claim is I'm not holding my arms in a very symmetrical shape. So, if you're someone who's sensitive to symmetry, you might say, well, gee, the universe might have some stuff you don't know about that looks like this. That is, it's things that have the properties of electrons, but also with the ability to pass through each other. Things over here that are force carriers, but cannot pass through each other. And if you superimpose those 2 pictures, you'll actually get something symmetrical, because you'll see them up and down here and up and down here. That X-shaped figure, that's a supersymmetric universe. That's the kind of stuff that people like me have been studying for about 40 years. We study it with equations. I wrote the first PhD thesis at MIT on this topic in 1977 because I was very fascinated by the idea. I knew that the universe had this part, but there were physicists saying it had this part. And I said, gee, how can it be that one is so lucky as to be born when the idea of new forms of matter and energy are being discussed? And all you have to do is study the mathematics. That's what I did in 1977. So now I've told you about supersymmetry. Supersymmetry says our world is composed of up and down quarks, charmed, strange, top and beautiful, electrons, there's neutrinos, muon, they're neutrinos, tau particles, and then a bunch of force carriers, particle of light, the W particle, which is the carrier of weak nuclear force, Z is a weak nuclear force, graviton, and Higgs particle. But in a supersymmetrical universe, this is me holding my hand in the other direction. There are a whole bunch of other things that we haven't seen. Now, these things are called superpartners. These are new forms of matter and energy, we've never seen them before, that may be out there waiting for us to discover, just like we discovered the Higgs boson. Now, they have, even though we've never seen them, we've given them names. So, for example, this is called an up quark. This thing over here is called an up squark. This is called a down quark that I'm pointing to. The object over here is called a down squark. This is our friendly electron upon which all our electronics is based. The object over here is called a selectron. Here is the muon. Its superpartner is the smuon. The photon sits here. It's the carrier of the electromagnetic force. In this more balanced universe, there's an object called a photino. My favorite particle in this perhaps structure of our universe is this one. You see, this particle is called the W particle. The name of this is spelled W-I-N-O. And I would just so dearly love one day to see a headline saying, W-I-N-O found in Geneva. Most people seeing that headline would assume that you're talking about an alcoholic specialist, whereas someone like me would say, no, it's the particle. They have found a superpartner particle. And so this is supersymmetry. It roughly says that we've discovered, in some sense, about half of what may be in the universe. Now, we don't know that this is actually right. That's part of what is going to be happening in the next 2 years, or rather, the next 5 years, once the LHC is turned on. People are going to be looking for this hidden part of the universe that we've never seen before. So now let me sort of leap ahead, because I'm going to show you some of the equations that lead to the existence of superpartners. This is what my own personal research that I've been involved in for the last couple of years. We've actually been able to use figures like the one you see here on the left to figure out the form of the equations that you see on the right. And in fact, in this supersymmetrical universe, we know how to start with these pictures alone and generate the equations that describe these superpartners and ordinary matter. Now, when you describe a new mathematical idea, you get to name it. Just like you name your children, you know, Sarah, Aaron, or Charles, or Francis, right? The parent gets to decide. So in science, when you describe a new idea, you name the idea. So Michael Fox was my collaborator, and we sort of stumbled upon this idea around 2004, that these pictures were the essence of the equations, and so we were searching for a name. And so Michael, who had traveled in West Africa long before I had, knew the word adinkra. It's a real African word, by the way. It comes from the Akan people in West Africa, and it's a word that means a symbol with hidden meaning. And you see, our symbols, which are the kind of things that you see here, have a hidden meaning, which is mathematics. So we've been playing around with these things, trying to understand their properties. Here's another such object. And as you can see, they can become quite beautiful in an aesthetic sense. Now, Albert Einstein said that at its highest levels, science and art become indistinguishable. And so maybe this is an example of that you can see art that flows from the mathematics of science. This is my favorite set of pictures. My wife keeps claiming she wants to have someone weave a carpet in these shapes and hang them on our wall, but we've not met a weaver yet to do this. And it all starts, as I said, with taking shapes and just playing with them. This entire set of complicated mathematics that may underlie this whole hidden sector of the universe that we've never known about, you can get to by playing mathematics. And in fact, I've been playing this with high school students. We've been developing this mathematics for the last 7 years, 8 years. A lot of times I have had high school students join my research group, and they have been the first people to discover mathematical properties. Or stated in the way of a novelist, they have found a story that no one knew before. Now, what's really interesting about this work is even though we've developed this, as I've talked to mathematicians, every mathematician I've ever talked about this work tells me that this is a piece of mathematics that has never existed before, which shows you something rather interesting about mathematics. You see, if I ask you the question, next week will there be more music than there is this week, you probably have an answer, which is yes. And the reason is because you know that somewhere, someone is creating music right now. Someone's making a new song. Someone's creating a new rap, a new concerto, a new concert, because we humans create music. If I ask you the question, next week will there be more mathematics than there is right now? That may puzzle you. Because see, most of us are not aware of the fact that mathematics is an element of the human imagination in precisely the same way that music is. Because right now, as we sit in this room, somewhere in the world, there's someone who is creating mathematics that has never existed before. And so yes, I've actually created a piece of mathematics. I and Michael, initially, and then others, we've created this piece of mathematics that was never out there before. So in that part, my wife is right. I make up stuff. Yeah, I do. But it's got to be mathematically consistent. And if it's good physics, it's got to imply something about the world. So one of the strange things of this story is, I've worked with high school students on this new piece of math. Just this past spring, the first mathematics PhD thesis on this subject was written. That shows you how creative mathematics is, that it's not something that only the mathematicians do, that people who are not mathematicians can create mathematics that then the mathematicians can come behind to understand. It's as fluid as writing stories, as making songs. It's what human creativity allows us to do. We do math like that too. So these are some of the stories. Since we're running a little bit long, I'm going to speed here. So these are the kind of the equations that come out of this picture-making story that I told you. You get equations like this. The thing that's interesting about this set of equations is this also contains Maxwell's equations, which tells us how electromagnetism works. Yes, Steve, it's a big surprise, but true. So these are some of these pictures. This is what it looks like when you start with just a little game with pictures that you can teach a student in high school, give them a few rules, and say, go play this game. And then as they play this game, they're actually doing algebra and calculus. Let me play this game for you a certain way. I'm moving the balls around here. In terms of the mathematics, this is what's called matrix multiplication. And for some of you who are undergraduates who may have studied math, you know kind of what that means. But in terms of pictures, this is what it means. You just move the location of an object in a symmetrical shape. It's matrix multiplication. I'm going to do an integral now. There it is. I'm integrating. For those of you who have taken a calculus course, wouldn't it be great if your teacher gave you this little device and said, go play this game, and you've learned how to integrate? That's what we're doing. Every time I lower a ball in this picture, integrals are being done. Each ball in this picture is actually a function. And now you can see there are actually two identical subcells here. That was not obvious at the beginning. I'm going to take these two subcells, and I'm going to smash them together. But I'm going to smash them such together that white balls go to white balls, black goes to black, blue links go to blue links, red links go to red links, dash reds to dash reds, solid greens to solid greens, perfect matching when I do the smashing. And now you can see it happening. I did it. Now again, this is like a game of Rubik's Cube in some sense. Very similar to Rubik's Cube. I can open this object back up. When I do that and look at the equations it corresponds to, it's this set of equations. Now the thing that's really interesting is that this is very different from the first set. Remember I showed you that first figure and I said these are things related to Maxwell's equations? I did something by playing this game, I get a different set of equations. Turns out the equations related to this is the Dirac equation, the description of how mathematically you describe the motion of electrons. It's the thing that when I was pulling quarks, you saw that thing at the top. That was about the Dirac equation. And so we've actually, in some sense, we've graphically represented a lot of the physics that people like me have done for a fairly long time. Now, let me get to something weird. There are computer codes hidden in this. What do I mean by that? Well, that first figure that I showed you, I can give names to. I'm going to call the bottom one 0, 0, 0. I only use 4 zeros because there are only 4 different color links. If I move along a red link, I'm going to change the first 0 to a 1. If I move along the green link, I'm going to change the second 0 to a 1. If I move blue, it's the third. And if I move along the fourth one, the black link, I'll change the fourth 0 to a 1. Suppose I did a red link and a blue link. That is, start from this location and did a red and a blue. So if I do a red, that would move me here. Then if I followed that by a blue, that would move me here. So doing red and blue from this place gets me here. But suppose I did blue first and then red. Gets me to the same place. So it's a game, right? It's a game you can teach any child. And now that folding up that I showed you, that weird folding up, I'm going to tell you about it in a different way. What happens in the folding is that this ball here actually gets smashed together with the ball down there. The ball over here gets smashed together with the ball up there. The ball sitting here winds up being smashed together to the ball over there. Can anyone in the audience tell me what's controlling the smashing? Say again? Complements, exactly. If you look very carefully, what you can see here is 1, 1, 1 went to 0, 0 because if you think of balancing these two things, putting the two together is how you get the balance. If you look at this ball, you see it has 1, 1, and 3 zeros. This one has 1, 0, and 3 ones. Again, if you're thinking about this balance, that's how you put it together. You look here, you see the first two entries are ones, and the last is 0. Whereas here, the first two entries are 0, the last two are ones. Putting them together accomplishes the balance. And so, this complicated smashing is actually about achieving a kind of balance once you decide to name the nodes in terms of these strings of ones and zeros. Now, when we discovered this, and this is work I did with 3 mathematicians and 2 physicists, we were stunned because this is the first time I've ever seen where codes actually show up in physics. You see, when you sit at your computer typing words or sending pictures or music, the computer doesn't actually send what you type. It actually sends ones and zeros. When you type at a computer, it converts the letters you type into strings of ones and zeros that computer scientists call words. And so when you do that with typing numbers or typing letters, it's all just ones and zeros. When you send a picture in a computer, the computer converts it all to ones and zeros. When you hear music from a computer, it's all converted into ones and zeros. The computer converts it and then reconverts it so that people at the other end can hear it. Digital communication is solely about ones and zeros. It's all based on strings of ones and zeros. All of our modern technology. This is the first time I've ever seen ones and zeros show up in physics like this. This is not about calculating an answer. This is about the structure of the equations themselves. When we first found this, I was stunned. Because it's crazy. It reminded me of something when I was much younger hearing about. There's a physicist named Wheeler who once came up with an idea he called it from bit. And his idea was basically that all of our universe is somehow about information. When I was young, I thought, what a crazy idea, but I didn't know other people thought he was crazy. Feynman, who was one of Wheeler's students, was talking to Thorne, who was another, and Feynman said, this guy sounds crazy, but what people of your generation don't know, because Feynman was older than Thorne, is that he has always sounded crazy. But when I was a student, I discovered that if you take one of his crazy ideas and unwrap it, like lifting layers off an onion, at the heart of the idea you'll find a powerful kernel of truth. This is Feynman about Wheeler. I remember hearing about Wheeler's it from bit when I was a young physicist, and I thought, that guy is crazy. How can it be the universe is all about ones and zeros? About 30 years later, doing my own research, what do I find? Strings of ones and zeros hidden inside of equations. So this to me was a very valuable lesson. It means that if you remain a theoretical physicist long enough, you too can become crazy. So do we live in the matrix? Nah, I don't know. I can't say that. But I can say that there's a digital substructure that we have found inside the equations if our universe obeys this balance, right? Because you have to be supersymmetric before these things emerge. We won't know if supersymmetry is there until the LHC tells us it has found some of these superpartners. So that's the way science works. Strange things have happened to me. I've been asked to tell this story on a number of occasions, and if you actually go to the website indicated here, you can find a long, different recitation of this story. I was invited to write an article for the British Journal of Physics World telling a story in 2010, and then life got really interesting. I was invited after that to speak at the American Museum of Natural History. Again, these are things that are online. NPR came to my door and said, "Gee, are you the guy saying that we're in the Matrix?" So there's a very long interview where I'm explaining what I'm actually saying. And then something happened interesting. You know, we live in a digital age. And old folks like me, we're not digital natives. We're immigrants into this land of digital technology. The young people who have been born into this technology, who never have a second thought of it, they're the digital natives, not people like me. Now, in this time of digital natives, young people learn how to do lots of stuff with computer technology and image and graphics and what have you. And so they can make you say things you didn't say. And this particular site is one such example. There's a young man out there who I've never met who created this website, which you can see the URL at the bottom. And at the website, he basically says, this guy, Jim Gates, says he's found scientific evidence. We live in the Matrix. Now, the way I found out about this site was rather interesting, because my kids came to tell me about it. They said, "Dad, we heard you have a new video out." And I'm like, "No, I don't have a new video out." Yeah, all of our friends are talking about it. You say we're in the Matrix." I'm like, "No, I didn't." I said, "Let me have the URL for this website." So they sent me the URL. And the first time I went there, I saw a picture like this, except that in the upper part of this diagram, Lil Wayne wasn't there. For you old folks who don't know this, Lil Wayne is a rapper. But the first time I went to this site, there was a guy named Snoop Doggy Dogg up there. And one of my kids' friends said, "Wow, your dad's on a webpage with Snoop. He's big time. He's blown up large." Well, I didn't interpret it that way. But it shows you in this digital age how careful you have to be about the way people use your words and your image to say things that you never said. And the thing that's really scary about this website, over 600,000 people have viewed this video as of now. If you go to Google and type in strange computers code discovered concealed in superstring equations, you'll find out that there's over 160,000 websites that are linked to that. It means that over 1 million people have watched this video of me saying things I didn't say. That's the danger that we live in this digital age, that people will manipulate your words and images to make you apparently say things you never said. On the other hand, I knew there was something weird about my work when a week after the British article came out, this website showed up. And then in this website, this young man asked a very provocative question, which is perhaps very appropriate for this venue. The question he asked is, so this Professor Gates has found evidence for digital codes, and they're, by the way, very special kind of digital codes that are called block linear self-dual error correcting codes. He says, this professor has found this evidence. If this is part of nature, who put these codes there? As a person of faith, he has a suspicion he perhaps knows the answer. And this was, to me, this is the first time I've ever done a research that has sort of kicked out a quasi-theological discussion. Is there a creator responsible for this code that we see evidence for? I don't know the answer to that question. But it's weird how science can lead you to such a strange place where people can ask such questions. There are actually 4 reasons I can think of for this code. One of them is it's all just an accident. Remember our story of Kepler? He had this beautiful story and it turned out not to be right. So maybe that's what's going on here. It's just all an accident. Another possibility, as that young blogger at Catholic Commentary hinted, is maybe we're the Sims in God's PC. Maybe he got it right. Then the crazy site that's been viewed by over 1 million people offers the theory that, well, gee, those codes are there because we really are in the Matrix. But I don't think any of those is actually the right answer. At least I don't know. As a scientist, the one that I find most intriguing is the following. These error correcting codes, which are these special strings of 1s and 0s that we've seen, you can ask the question, where else in nature are error correcting codes seen? It turns out there's some evidence that there's one place in nature where error correcting codes have been seen. It's in genetics. Because you see, when you think about the stability of genetic systems as they reproduce, normally mutations occur. And if mutations are allowed to run wild, then you don't have a stable genetic structure in which to propagate a species. There is some evidence that error-correcting codes are in action in our genetic code. And so, if we take that as our model, because normally when I'm confronted with a question about nature I don't know the answer to, I ask, is there something similar in nature where she has provided an answer to us? So to me, this is the most intriguing possibility, that the error-correcting codes that we see in these equations are somehow evidence that something like natural selection has occurred in the laws of physics itself. Not in biology, but in the laws of physics. Now, I don't know how to prove this either, but to me, this is the thing that's in the strongest scientific tradition of finding a piece of evidence and then looking at all the possibilities and then looking to nature to provide guidance when you see something you've never seen before. I showed you this picture earlier, and I asked you a question to which one you liked most. Can I see how many liked the picture on the right most? Show of hands, please. Don't be afraid. It's not, look, it's a pop quiz, but you're not going to get graded. Hands high. Okay. How many of you like the picture on the left most? Interesting. This is very interesting. If you look very carefully at these two pictures, you'll notice there's a mole here that also occurs there, which means that that's not actually a picture of me. Because if you look at my face, there's a mole on one side, and you can see that in this picture. Now, the reason I did this experiment is because many years ago, there have been series of experiments done by psychologists where they will take a face, cut it in half, make the mirror image of one half and then glue the two back together. And that's actually what you're looking at on this side. I did this myself because, you know, we can play with computers and do such things. And then I've been asking people, gee, do you have a preference for these two? Now, what's really interesting to me is, as I took a count here, you folks actually all picked, the majority of you picked the left, not the right. But the left side is, in fact, the side that is the real picture, not the more balanced picture. So my conclusion is that this audience is out of whack. Thank you. Thank you.
Thank you, Professor Gates. We will take some questions now for a few minutes. We'll have some portable mics to pass around, so we'll just take a second to get started here, I think.
So I have a number of people I normally think. My collaborators obviously made enormous contributions. I could not do this without my collaborators. Science is a very collaborative process. It's not something that you go in a corner and do by yourself. And so I acknowledge all of them. My students obviously have worked with me very diligently for me to be able to tell you this story of science. I also have to thank the company called the Teaching Company, because in fact a lot of the graphics in my presentation come from a DVD I did with them called Superstring Theory, the DNA of Reality. And then finally, there's a gentleman by the name of Ken Griggs who created a number of those illustrations. And Ken Ferguson, who created the folding diagram. That folding diagram is mathematically correct, and I actually worked out the mathematics and worked with the graphic artists to make sure that we got all the factors of minus signs and the zeros and the plus signs and everything correct. So I have to acknowledge the work that those people put in. Okay, so where's the mic? Yes, sir.
My name is Dwayne King from Golden Valley, Minnesota. And first off, Dr. Gates, welcome back to Minnesota.
Thank you.
And a question I would have, and I think there was just one little allusion that might lead to it, but how does what you say here then relate to string theory?
Ah, yes. So it turns out, so I've kind of introduced this audience to the notion of supersymmetry by saying I'm trying to get the balance X to occur. That is, in our world, we have force carriers that are kind of up here. We have things like the electron kind of here. They have different properties. Imagine a mathematical world where in addition to this, there's that. That's how I introduced supersymmetry. Well, it turns out that string theory, at least all the string theories that are mathematically consistent, have this property of supersymmetry. So it's not divorced from string theory. It seems to be an enabling foundation for the construction of string theory. In fact, we physicists typically talk about string theory as superstring theory, and the super is actually supersymmetry.
Hello.
Hi.
Press something?
No, I can hear you.
Okay. My name is Mike, and I'm a retired psychologist and,
Ah.
and a poet. And my question is part of the story when you had
You have to hold the mic to your mouth.
part of the story when you had the two screens there with the opposites of each other,
Yes.
the complementary. Does that tell part of the story of dark energy or dark matter?
Very interesting question, and a lot of us think the answer is yes. Let me go back to that particular slide, because that's a very astute observation on your part. You try to get this to activate again so we can bring it up. Please, there we go. In a moment, there we go. So this is what we see here. What we see here are basically all the particles that we know about in our world. And yet, if the world is supersymmetric, there's this other stuff that we haven't gotten to. Now, in our world, if you stop and think about it, everything doesn't have the same mass. I mean, the mass of the proton by certain units you can say is about 938 in some set of units. In that same set of units, the mass of the electron is about a half. Well, a half of an MeV is the words. So, if in our world, which is on this side, everything doesn't have the same mass, some things are heavier than others, then there's every reason to expect that in this mathematical world that we see over here, everything all over there shouldn't have the same mass either. Some things should be heavier, some should be lighter. In particular, there's something over here that you expect to be the lightest object on that side of the picture. If that thing exists in nature, it makes for an excellent candidate for dark matter. Now, there's some other caveats, but this is one thing that the physics community has been aware of for over a decade, and that's part of the reason why so many people are interested in supersymmetry, because without doing anything except, remember, this story starts from we just want balance, and then magically you get out dark matter.
First, I'd just like to thank you so much. I found it absolutely fascinating. It's just insane. But I have
I agree.
Thanks. I have a question, and I don't mean to gush, sorry. But I have a question. What exactly is a quincunx?
I was wondering who was going to ask that question.
Yeah.
So the point is the following, because I didn't deal with that, and I never do when I give this talk, because I want someone in the audience to ask, why did I use that word? Well, first of all, quincunx means fivefold. And so if you actually look at the topic of this talk, what we saw was the following. We saw science. We saw art, because it leads to these graphs. We saw discussions of theology. We saw computer science. And we saw science fiction. So it's this discussion was at a fivefold nexus, or a Quincunx nexus.
Hi, Dr. Gates. Can you hear me here?
Yes, I can.
Well, I was actually wondering something that I don't want to take your analogy too far with biology, but as I'm sure you're well aware of biology, even though it's self-correcting, there's also room for things called mutations. Which,
Absolutely.
Even though they may be harmful, in some ways they can be beneficial and come to something that is even better than was before.
Right.
So does your intuition say that possibly your self-correcting equations might not be perfectly self-correcting but allow for mutations?
My suspicion is that they must be perfectly. So this is the part that now I'm going into real speculation, and I don't know how to prove this, but my intuition is the following. If I ask myself, why in the world would the universe, the entire structure of the universe, why in the world would error correction codes be important? The thing that occurs to me is, first of all, the universe started with something called the Big Bang. At the time of the Big Bang, densities and temperatures were enormous. That means that any structure that could come into existence was subject to be destroyed because of the fluctuations in the environment. And so, in such an environment where even the force laws don't exist, and where particles don't exist, but you have enormous fluctuations in energy and temperature, you might say, then how does any structure at all stabilize itself? One thing that I can imagine is that the error correcting codes that we see in evidence of supersymmetry could in fact have been the mechanism by which the universe would stabilize its entire existence at the smallest instant of time after the Big Bang, where fluctuations were violent. And in other words, and why I don't think there would be other mutations, because the way natural selection works, as you said, is you can get mutations. Some of them are more beneficial than others, but ones that are less beneficial don't survive. And so what my suspicion is that anything else that the universe might have tried to do was in fact not viable. And that's why we would be left with a universe that had coding in its structure. Now this is speculation, and I've actually not written about this in any scientific paper, but this is my intuition about what it means.
Other questions? Great, I'm bringing the mic up.
Yes, Dr. Gates. I was wondering if there is a super complement to a black hole.
Basically, just a moment. Black holes in the mathematics of supersymmetry are allowed. I am not aware of anyone who's actually pursued it to the extent of saying, suppose the matter that actually caused the black hole was actually part of the superpartners. I don't know of any scientific work in that direction. I don't know of any prohibition against it. There's a hand up here, Chuck. But everybody else wants to hear, I think.
If you are saying that it's symmetrical, where you just flip it over, how do we know that there aren't more lines of symmetry? So to
Great
say?
question. No, great question. In fact, physicists have actually studied that question over the course of the last decade. Supersymmetry, which is sort of the flipping that I'm talking about, is the first of something that is the first example of what's called a supergroup. Earlier I talked about symmetry and I mentioned the name Sophus Lee because he's a mathematician who at the end of the 1890s gave the math community a description of how symmetry gets realized in math, which we physicists around the time of Gell-Mann actually borrowed. After supersymmetry was discovered, people started working on other things, asking precisely the question about whether there could be more flipped axes, or more axes of symmetry, as you refer to it. And when you study that, what you find out is that the mathematics, it's called quasi-statistics. Q-statistics, that's the word. There's a whole literature on Q-statistics, and what you find is that the mathematics there tends not to be as rich as the one that only has this twofold axis of symmetry. And so this is a line of research that, although for a while it was popular, there's almost no one studying this now. The evidence is that it doesn't lead to something that's viable, as rich. Great question.
Any others? All right, let's thank Professor Gates again.
Thank you.